So this is my lab report for Lab 2, motion of a falling object. To introduce this lab, my purpose was to observe the y coordinate of an object like a ball that I dropped from a certain height, and you can find its velocity, and then compare that to models that also predict the position and velocity of what it thinks is that ball. With two models. So when gravity is present, and then when gravity and drag are present forces that add up to the net force. Model I used was I dropped the die from a height of 29 inches. So the fundamental principles that I used for this lab were Newton's second law again, which is the change in velocity over change in time equals the net force over mass. And then the velocity update and position update formulas can be derived from this. Second, I used the force of gravity idea. So the force of gravity is equal to 0 in the x and z direction, but negative mass times the acceleration due to gravity in the y direction. And then the drag force equation, which I was only concerned with the y direction for this experiment, which is equal to negative b. B is a proportionality constant that is found through trial and error, times the y velocity, which only matters in the magnitude sense for this experiment. So the magnitude of velocity squared times the direction of velocity. This is the video I recorded of dropping the die from the top of my desk. And then this is the tracker. So I tracked this video and the die's movement. So I found I started tracking at about 0.561 seconds, and I stopped tracking at 0.957. So this change in time was about 0.4 seconds. So from start to finish, from 0 to 0.4 seconds. This is the table that I got tracking that position. There were about 13 observations in total, including that initial condition, the 0. The change in time each time was 0.033 seconds. The y, as you can see, is not linear. It increases at an increasing rate. The acceleration is increasing. And then the x, the x doesn't matter because it's not what we're worried about in this experiment. We're dropping it from a height as it's going from higher to lower. Same thing, don't worry about the x, but the y graph is important here because, like I said, it's slow to get going at the beginning. As it nears the end, though, it's accelerated a lot and its velocity is higher. So as for the coding part, so for my gravity-only model, my initial conditions, I had the ball mass at 5 grams. I started the position at 0. Velocity was also at 0 because it was in my hand. Delta t at 0.033333. And then the gravity equals 9.8, and the proportionality constant doesn't matter for this model. The calculation loop, I had t less than 0.399. I did this instead of 0.4 because it kept going. It kept going past 0.4, and I didn't want that extra data point. The only force here is gravity, so gravity does equal F net, and then these are the velocity and position update formulas here. Next, I have the conditions and loop for the gravity and drag model. So everything here is the same, except for that proportionality constant, which I found the one that best fit my data was 0.0075. Then into the calculation loop, the only thing different here is that I added a drag force, and the gravity can't be F net anymore because it's gravity plus the drag force, in which, like I said, this is the direction. This is the magnitude squared because y is the only one to account for, and then this is the negative b part. So comparing these two graphs to each other, because it's just gravity, this first model is dropped at a much lower point at 0.4 seconds than this one is. So it's at only negative 0.65, whereas this one's at about negative 0.85 because this one has an upward force that's causing it not to go down as much. And then here is where I compare, and I found that the gravity and drag model represented my experimental data a lot better. To wrap up and have some discussion questions. So the first one, is there a model that predicts a terminal velocity? The answer is yes. The gravity and drag model can, and as I found in the second question, predict a terminal velocity where the force of gravity equals the force of the drag, and then that means that there would be a constant velocity, which happens at around here. For the second question, if there was an initial downward velocity. So in this case, I think I chose 0, negative 5, 0 for the initial velocity. It still ends up at the same velocity, around negative 2.5, and it happens at the same time. Next, and lastly, I have some possible sources of error. So due to my experiment, if the die hit the desk at all when I dropped it, it could have affected velocity and maybe some of the drag force. And then if my hand was moving or shaking, that could have also made the velocity not zero. And then lastly, for modeling, that B value could be incorrect. It could have been more closely approximated.